So arc length and area. Here's a circle. First of all, the definition of a sector. It's a piece taken out of a circle, but it's the piece that's been cut from the center. So the lengths of the sides of a sector are r, the radius of the sector. So in other words, this is not a sector, okay? It's a segment, yeah, that's been cut out of the circle. A sector is measured from the center. We've already defined, but we might as well put it on here as well, that this distance here, round here, from there to there, for example, is the arc length. So arc length is this distance measured around the outside of a circle from past the sector, and then the sector is the area. Well, we've got the area of the sector in the middle. So that's the definition in terms of the circle. And there's two formulae that we can use. We can derive where they come from, but I'm not going to worry about doing that. Let's just write them down. We've got two formulae. One to find the arc length, and that is very straightforward. It's just the radius times by the angle, but that angle must be measured in radians. Otherwise, the formula doesn't work. The reason why that formula works is because the radian is defined as part of this circle, this distance around a circle. And the area is a half times the radius squared times the angle. Again, angle measured in radians. So there's two formulas that we use, and I'll just present them to you. So if I wanted to know the area of a sector, all I need is the radius and the angle measured in radians, and I've got it. I could rearrange the formula. So if I knew the area of the sector and the angle, I could find the radius, and so on. So example, find the arc length and area of a circle with radius 1.9 centimeters and angle 45 degrees. Okay, so if we want the arc length, we're going to use the formula S equals r theta, but theta must be in radians, so the first thing we do is convert our angle of 45 degrees into radians by using that conversion, 45 times pi over 180, which gives us pi over 4, or 0.785 radians to three significant figures. So now I just use the formula to find the arc length, so that's going to be 0.785 times the radius, which is 1.9. And that gives us the arc length. It's as simple as that. All I've got to do is, if the angle is not in radians already, convert it to radians. And that gives me an answer of 1.49 centimeters. We could use it. We could go to 3, or we could say 1.5 centimeters to two significant figures. We want the same significance as in the question. So the arc length is about 1.5 centimeters. Similarly, the area is a half r squared theta. So that's going to equal a half, or 0.5 if you like, times the radius squared times theta, 0.785. So again, just plug those numbers into the calculator and out comes the answer, which is 1.42 unit centimeters squared, because it's an area, and this has been given to me, the three significant figures. Agreement there? So now I want to look at circular motion, which is probably the main use of the radian measure and the one that you'll be using the most within your engineering course. This idea of rotating objects. So let's look at this circle. And consider this point here, rotating round in a circle, going round here like this. We tend to consider things going around anti-clockwise. So this point, this red dot, is rotating round in an anti-clockwise direction around like that. We consider it as being on the end of a vector. So this is a vector, and so we often talk about a rotating vector. So after a period of time, this vector has moved round to here, this point has moved to here, and it's gone through an angle theta. So after a bit more time, this rotating vector might have gone round to here. So there's the point, and the angle is here. We always measure angles from this positive x-axis. So we've got this idea of something rotating around. And you can see obvious uses of this in crankshafts, in machinery, anything that's got a point that's rotating, going round. Then there's a relationship between how far it's gone round in this circle, but also how far it's moved, say in this direction, or less commonly in the x direction. We're more than often interested in how far this dot has moved in this y plane here. So if it's gone from here and it's moved round to here, then it's moved that distance up in the y direction. By the time it moves round to here, it's moved this distance in the y direction, and so on. And then it comes round here, and now it's going in the negative sense here. So we talk about it going up and down in this y plane like this. And that's something for next time when we talk about the sine wave that I want you to think of, because I'm not going to be here next time. I want you to look into the sine wave, which is to do with this, and the cosine and the tangent. And then when I come back, I'll sort of bring that all together. But just for now, let's think about defining a few things about this circular motion. First of all, the rate at which this point is moving around the circle in an anti-clockwise direction is given by its angular velocity, omega. We use this Greek letter omega to represent angular velocity. It looks a bit like a W, but it's curly. So if you were to wanted to draw an omega, you draw it like that, sort of a curly W. Omega. Part of the Greek alphabet. So call it omega, don't call it anything else. And it represents the angular velocity of this thing as it rotates anti-clockwise. So if it was going round clockwise, we could talk about an angular velocity, but it would be negative going clockwise. We can also define something called frequency. F. And that's the number of complete revolutions or turns per second. The frequency. Units, we measure angular velocity. If we think about angular velocity, as we talked about a second ago, time goes by. So at time 0, here's where my point is. My vector is in the horizontal plane. Later on, you might talk about something starting at not at this point, but maybe over here. In other words, there's a phase lag between one and the other, and so then we start talking about phase differences. But for now, we're going to talk about it starting off here at time 0. So after a period of time, it's moved round to here, and here's the angle, theta, as we've talked about, okay, measured in radians. So The angular velocity is to do with the rate at which this angle is being swept out. Just like linear velocity is to do with how far you go per second, the angular velocity is how much angle you turn through per second. So it's measured in radians, because that's what we measure the angle in, per second. So that's what we measure angular velocity in. And frequency, number of turns per second, measured in hertz, Hz, which you've used, I'm sure, already. So we measure frequency as hertz, cycles per second, turns per second, and we measure angular velocity in. Now, in terms of radians, what's a complete turn? 2 pi, okay? So what I want now to come up with is a relationship between this frequency and the angular velocity. Guys, relationship between the frequency and the angular velocity. Angular velocity is how far it's moved round here in terms of 2 pi. So if it manages to go, say, 1 complete turn in a second, then the angular velocity will be 2 pi radians per second, because 1 turn is 2 pi. Agreed? If it manages to go 2 complete turns in a second, then that will be 2 lots of 2 pi, which is 4 pi in a second. So the angular velocity would be 4 pi radians per second. Agreed? If it goes half a turn in a second, then that's 0.5 times 2 pi, which is pi radians per second. So the angular velocity is to do with just how far around it goes per second. But if it goes 2 complete turns in a second, or 3 complete turns in a second, what's another name for that? 3 turns per second. What have I just defined? The frequency. So if you think about it, the angular velocity is just 2 pi, which is 1 turn, multiplied by the number of turns per second, which is the frequency. So we have a formula that relates the angular velocity omega and the frequency. Omega equals 2 pi f. And that's a formula that you will use. And it just comes from the definition of angular velocity and frequency, and our knowledge that a complete turn is 2 pi radians. So again, because of this 2 pi, that tells us we're talking about radians. So as soon as you're talking about angular velocity and it's measured in this unit, your angle must be in radians, otherwise you're not going to get the correct value for angular velocity. It must be, there's no choice. Angles are measured in radians by definition to be able to use this formula for the angular velocity. Now, linear velocity, v, so this is the linear velocity, we know what that is, it's just distance travelled per second, isn't it? Meters per second. If I go 1 complete turn in a second, in terms of distance, in terms of meters, how far has this thing gone? What's the formula for the circumference of the circle? Formula for the circumference of a circle. Pi d, yeah, or in terms of r? Yeah, pi 2r or 2 pi r is often how we say it, but exactly the same thing. Pi times 2 times r, or 2 pi r, okay? 2 pi times the radius. So if this thing goes 1 complete turn in a second, it's gone a linear distance around the outside of this circle of 2 pi times the radius. If it manages to go 2 complete turns, it's gone a linear distance of 2 pi r times 2, hasn't it? Because it's 2 turns a second. And that's the frequency. So in other words, linear velocity, v, measured in meters per second, is related to angular velocity. And I'm sure if you think back on this video and what I was just saying in terms of how far it's gone, literally around the circumference of a circle, you could work out, and I'm not going to do it for you, you can do this for yourself if you like, but actually the linear velocity is the angular velocity times the radius, and that's the other key formula that we use when we're talking about angular motion. We talked about the formula that relates the frequency to the angular velocity, omega equals 2 pi f, and we talk about the formula that relates the linear velocity v to the angular velocity omega. And that's a very common formula to use, because it's not uncommon to have situations where we have something rotating with an angular velocity omega, and in some sort of process you might be then pushing out material along a belt or something with a linear velocity v. And this formula relates those two things. If I know the radius of this drum that's producing this material, for example, r, then there's a direct relationship, and here it is, between the angular velocity of the drum and the linear velocity of the wire that's been extruded, or the conveyor belt that's moving in this process. Okay? So that's a very important formula that relates these two ideas, angular and linear velocity. And we can use them to solve problems. So I'm now going to give you a handout with some problems on that you can have a look at. So this handout appears under assignment 2 on the website. So if you go to assignment 2 under the notes, you'll see this handout on linear angular velocity. That summarizes what we've just been talking about, the idea of radians, angular and linear velocity. And then on the second side, there are some questions that you could have a go at. Okay? Right.